Okay, this is a recording of the Solutions 2 1-2A worksheet. On the first page of this worksheet, I'm going to do this from a PDF file that should be pretty consistent throughout the year. I can try to highlight and put some text in as we go, but most of it is written down. On these first four problems, you'll probably find that we did not really see examples like this in the notes, but this is really a skill that is still expected. So, let's read through this. Write a function for the area A of a circle as a function of the diameter. Most of us know the area as a function of the radius, but now it wants us to write the area as a function of the diameter. So really what we need to do is just start with the formula we know, the area is pi r squared, and now we just have to rewrite this. Instead of being an area as a function of r, we want it to be an area as a function of d. Well, is there any way that I can relate the radius and the diameter? Right here. It's called a relating equation. 2 times the radius equals the diameter. So the radius is 1/2 the diameter. And I just plug that in right there for r. So this, and if you can follow my cursor, is coming right in here for r. And then I'm squaring it. If I square 1/2, I get 1/4. If I square d squared, okay, I get 1/4 pi d squared, okay? Pi over 4d squared. And then lastly, it says find the area of the circle with a diameter of 4. So now I can plug 4 in directly. 4 squared is 16. 16 divided by 4 is 4 pi. Okay? And that's how all the rest of these three are going to work, are along this line right here. So let's move on to problem number 2. And again, you can pause this video, work back and forth to get it written down, go back and listen to anything that I might say. Write a function for the height of the equilateral triangle as a function of the side length. Find the height of an equilateral triangle with a side length of 3 meters. So first of all, let's just draw an equilateral triangle. We know that an equilateral triangle is also equiangular from geometry, so each one of these angles has to be 60 degrees. We also know that if we drop down the altitude, I called it h in this case, if we drop down the altitude, it's always going to split this vertex angle into 2 equal angles that are 30, 60, 90, right triangles now. And so if we look at this as being 1/2 of s, because I took s, I had to split it in half, it's 2 equal sides, it bisects the base. I know from my 30, 60, 90 relationship in trigonometry and geometry that if I have the side opposite the 30-degree angle, I simply need to multiply it by the square root of 3 in order to get the height. So if I take 1/2 of s times the square root of 3, there it is, square root of 3 over 2 times the side length. Now I have the height written as a function of the side length. So you can give me any side length and I can now tell you what the height is of that equilateral triangle. They asked me to then find the height of an equilateral triangle with a side length of 3 meters. So I plug 3 in. 3 squared is 3 over 2. Don't forget units of measurement anytime that they give. It probably would have been better if I wrote out meters here. Problem number 3. Again, I leave it here for a little bit so you can get the work down. Write a function for the surface area S of a cube as a function of the length of the cube's edge. Then find the surface area of a cube of an edge length of 5 feet. Let's just start with what we know. Well, maybe you don't remember the formula for the surface area of a cube. So let's draw it. Nice cube here. You could think of a die. All these edge lengths are the same. It tells us to call the edge length E. Instead of S, we're calling it E. Well, here's what I know. The area of the front is E times E or E squared, but the area of the front is the same as the area of the back, which is the same as the right side, same as the left side, same as the top, same as the bottom. All 6 faces have an area of E squared. So I just multiply that by 6. Some of you maybe have this memorized. That's okay. Then you just write it down. And then they want you to find the surface area if the edge length is 5 feet. 5 squared is 25 times 6 is 150. Don't forget it's feet squared. That's why I was writing down the units. Problem number 4. Write a function for the volume of a sphere as a function of the sphere's radius. This is really just, do you know the formula or not? Hopefully you remember it from geometry. The volume of a sphere is 4/3 pi r cubed. We will actually prove this later on in chapter 8 by taking a quarter of a circle and revolving it and then doubling it. It's a great application. Then it wants you to find the volume if the radius is 3. 3 cubed. Again, I'm going to talk through this to make sure. 3 cubed is 27. 27 divided by 3 is 9. 9 times 4 is 36 pi. Don't forget, volume is units cubed. Okay, hopefully everybody has that down. Then we get into these graphing problems. In addition, I also ask you for things like domain and range and those types of concepts. But let's just start with just this much. If I wanted to plot this, we can point plot this. If I plug 0 in, 0 minus 9 is negative 9. Whether it's positive or negative 1, when you square it, it becomes positive 1. Minus 9 is negative 8. Whether it's positive or negative 2 squared is a positive 4. 4 minus 9 is negative 5. On down the line. Okay, I shouldn't have to talk through each one of these. I think everybody's good. Notice, if opposite signs produce same result, opposite signs produce same result, opposite signs, it's an even function. That's why this graph is symmetric about the y-axis. We could fold this graph over the y-axis and have the mirror image. I also ask you for some of this other information. Remember, I have this set up for you. This is why I created the worksheet, so you don't have to write down a lot of extra notation, except for you to know how set builder works compared to interval. Set builder notation. X is the element of all real numbers. Make sure you use braces. Make sure it's a double-lined R. This is a curved E, but that's how we read this. X is the element of all real numbers. Okay? And it's a set. That's why we have these braces. In the future, you'll just be able to say X is the element of all real numbers. Do not write ARN. I know that that's been allowed in some of the classes in the past, which is fine. It's just I've never seen it on the AP test, and we want to be consistent with the language that they will be using. Either write out all real numbers, or you can use this notation for sure. The domain in interval notation, then, anytime it's all real numbers, is negative infinity to infinity. Never, ever, ever brackets on infinity. It's always parenthesized. The range of this, when I plot point this, look what the range is. The range starts at negative 9 and goes up from there. Therefore, y is the element of all real numbers such that y is greater than or equal to negative 9. That's how we write it in set builder notation. Remember, this line means such that. This means real numbers. This is the element of real numbers. Since I have an equal to here, that's why this is bracketed negative 9 to infinity. I can get my x and y intercepts out of my t-chart, but remember, anytime I want to find a y-intercept, I plug 0 in for x. Anytime I want to find an x-intercept, I plug 0 in for y and solve this. Whether you solve it by extracting the square root or by factoring, okay? And we actually stumbled upon all of the intercepts just by doing a good point plot. That's why I want you to practice. Point plotting is somewhat of a lost art, and I think it's a great method for plotting functions like this one. Some people maybe don't know exactly what this is going to look like to start with. So let's point plot it. I can plug in 0. Negative of 0 is 0. Square root of 0 is 0. Negative 0 is 0. I get 0 back out. I cannot plug 1 in for x because I cannot take the square root of negative 1. It's an imaginary number. I have to only plug in negative numbers. And I want to think of perfect squares. So I'm going to plug in negative 1, negative 4, negative 9. That's why I gave you these 4 boxes. The negative of negative 1 is positive 1. Square root of 1 is 1. Make it negative. The negative of negative 4 is 4. Square root of 4 is 2. Make it negative. The negative of negative 9 is 9. Square root of 9 is 3. Make it negative. There are 4 quality points that we can graph. But we need to remember that even roots, square roots, fourth roots, sixth roots, They have endpoints. They do not have asymptotes. They have endpoints. And that is the endpoint. And then I sketch this. This square root is simply the bottom half of a sideways parabola, because that negative sign right there made it the bottom half instead of the top half. If this negative sign was missing right here where my cursor is, it'd be a similar look, except it would be the top half of that sideways parabola. Notice both the x and the y-intercept are the origin, and you could solve those again. Plug 0 in for x, figure out y-intercept. Plug 0 in for y to figure out x-intercept. Domain. Notice here, the x values are less than or equal to 0. Since the domain is less than or equal to 0, remember, anytime it's less than, if you notice some pauses in, I'm trying to pause it every time that there is an interruption over the intercom, which you know is quite frequent around here, but I'm going to try to do that each time so that we don't have that interruption. But I'll try to get it as fluid as possible. But remember, anytime it's a less than situation, you start with parentheses, negative infinity, because it goes on forever to the left. Comma, the larger number goes on the right, but this time we want to stop. Just think of a bracket is a stop, but it also means included. That means 0 is included. If there was no equal to there, we would go parentheses. The range. Range sometimes gives students difficulty. You really need to know what the picture looks like, because I have to see my y values. My largest y value is 0, and it goes down. So the y value starts at 0 and goes down forever. It goes down slowly, but it goes down forever. So y is the element of all real numbers, such that y is less than or equal to 0. Parentheses, negative infinity, comma, that is a 0 with a bracket. Okay? That takes care of everything on that particular function. Notice any of these functions, since they are functions, can be typed into your graphing calculator to check. Hopefully you know how to use your table key as well. I'm not going to do a lot of the calculator work unless it's something that I really think you need to see on the calculator, and I will call it up in that case whenever we're doing these videos. Problem number 10. Again, this tends to give students some difficulty because of this negative sign right here. So I showed the work for you. In case you can't see it, let's do the domain right away. Anytime that you want to find the domain of an even root, not an odd root. An odd root, we can take the odd root of negative numbers, but if it is the domain of an even root, a square root, a fourth root, a sixth root, just set the argument greater than or equal to 0. If I divide both sides by a negative, don't forget we have to flip the direction of the inequality. That's why it becomes x is less than or equal to 0. You can discover the domain by just trying to point plot as well. But sometimes it's nice to know the domain before you start. So here it is written in set builder notation and then interval notation. Notice parentheses always on the infinities. Negative infinity to 0 bracket. Okay? Now when I'm point plotting this, I plug 0 in. You have to remember that you can take the root of 0, whether it's an odd root or an even root. Okay? The fourth root of 0 is 0. But I cannot take the fourth root of 1. I can plug in negative 1 because if I negate negative 1, it becomes positive 1. And the fourth root of 1 is 1. But now you have to think, I don't want points that produce decimals. I want a good quality point. And really the next good fourth root is 16. So I have to plug in negative 16. So when I negate it, it becomes the fourth root of 16, which is 2. And I have to, this is off the graph here a little bit, but that's the next really good point to start at 0 and go this way. Again, even roots are half of these sideways quartic functions in this case, a fourth root. Okay? So just picture, I'm just looking at the top half because there's no negative sign out in front. If there's a negative sign out in front, it would have been the bottom half of that quartic, sideways quartic. X-intercept, y-intercept are both 0, 0. There's a nice picture of it. Pretty straightforward. All right, now we get into rationals. And with rationals, the biggest thing that there's a lot of key factors here that you have to know. It may be helpful for some of you to write this all as one fraction. Because some of you know a rule from pre-calculus that said if I want to identify the horizontal asymptote, I'm going to consider one of three factors. If the degree on top is less than the degree on the bottom, y equals 0 is always the horizontal asymptote. If the degree on top is the same as the degree on the bottom, then I look at the coefficients of those highest degree terms. So 1 over 1, I look at those ratio, which is 1. So this actually has a horizontal asymptote of y equals 1. But you can also tell it from here. Look at the degree on top is less than the degree on the bottom. This goes to 0, but 1 plus 0 is 1. That's why the horizontal asymptote is y equals 1. So you have to decide, is it easier for you to identify the horizontal asymptote from this, written as two separate terms, or if I have it as one ratio, one numerator, one denominator, and then use the rule that you learned in pre-calculus. Okay? But the horizontal asymptote in this problem is going to be y equals 1. The vertical asymptote here is x equals 0. Notice, I can't stress enough, if the vertical asymptote comes from a factor raised to an even power, it creates this volcano look. It's not a pole. If this was x cubed, then it would be a pole you'd have to slide down before you start the graph again. But if it's a volcano, you come and you jump over the asymptote and start again. So that's why I identify down here the vertical asymptote as x equals 0, and I call it a volcano. I'm going to try to be as descriptive as possible on my keys, where the horizontal asymptote is y equals 1. The degree on top equals the degree on the bottom, so I'm looking at the coefficients of the highest degree terms. Or this goes to 0, and 0 plus 1 is 1. Either way, you get y equals 1 as the horizontal asymptote. Okay? The domain and range we're going to deal with after we point plot this a little bit, see what's going on. Notice, it doesn't matter whether I plug in plus or minus 1, I get out the same thing. That's why I listed my values like this. It's an even function. Opposite inputs produce same output. Opposite inputs produce same output. Even function. If I plug in plus or minus 1 and square it, 1 over 1 is 1, I get 2. You can look at each one of these and see these results. If I square 2, I get a 4. 1 plus 1/4 is 1/4. Squaring 3, I get 1 and 1/9. If we were to look at another one, if I plugged in 4, I get 1 and 1/16. It's getting closer and closer and closer to y equaling 1. That's why it is a horizontal asymptote. And we're going to talk about that in more detail in Chapter 2. So how do I see what happens then with this volcano look? I got to pick a number between 0 and 1. So I show a couple here for you. You do need to be able to do this. If you plug in 1/2 and square it, you get 1/4. 1 over 1/4 is 4. And 4 plus 1 is 5. You can do these. Plus or minus 1/3. When I square it, I get 1/9. But 1 over 1/9 is 9. 9 plus 1 is 10. So I can see as I'm getting closer to this vertical asymptote, the numbers are going larger and larger. They're approaching infinity. That's how we're going to define a vertical asymptote. And I get the same look on both sides. But you can point plot these, and you have to practice this. The only way to get better at computation is to practice it. To not jump on the calculator right away, but to practice it. So looking at this picture, domain, even from here, there really are two main considerations you got to look for now for domains. And we'll add to this. But am I taking the even root of a negative number? No, there is no even root here. Do I have the possibility of dividing by 0? Yes. If there's a variable in the denominator, I've got to make sure that I'm not dividing by 0 because that is undefined. So x cannot be 0. That's why we get this vertical asymptote. Here's how you write it in set builder notation. X is the element of all real numbers such that x cannot be 0, equal to 0. So this is not equal to. That's the best way to write it. It's kind of awkward in interval notation, but here's what it would look like. Parentheses on negative infinity, always, parentheses, comma, 0, parentheses, because I don't want to include it. In union, parentheses, start with 0 again, go to positive infinity, parentheses. I'm not including 0 because it's parenthesized on both of these intervals. That's how you exclude something in interval notation. This is why we want to know both notations. Interval notation is definitely the shorter notation in many situations, but in this one it's actually longer. So we would want this one, okay? Because eventually we're not going to do the set stuff. We'll just say x cannot be 0 and that'll be good enough. I only want you to know set builder because it's used a lot in upper level mathematics, particularly when you get into courses like abstract algebra, real analysis, those types of things, okay? The range, look at this. These y values never hit 1. It gets closer and closer and closer to 1, and they go up forever. That's why I have this arrow right there. So the y values are greater than 1, but they're not equal to 1. Y is the element of all real numbers such that y is greater than 1. There's no equal to. That's why it's parenthesized. Comma, infinity, never, ever, ever. Brackets on infinity. Always parenthesized. Okay? Problem number 14. And again, you can kind of move back and forth, pause if you need to. On this problem, I like to start with the domain on a lot of these. It's an even root. So I know it might have a domain restriction. I need to make sure that the argument is greater than or equal to 0 because I can only take the square root of non-negative numbers. If I add x to the other side, that's the same thing as saying x is less than or equal to 3. The alligator is eating the 3, not the x. There's my domain. So I start at negative infinity, I go up to 3, and I bracket because it's included. That helps immensely because now I know what numbers to plug in. Remember Mr. Hearn and his topic of most interesting value of x. I couldn't agree more. When you plug in 3, because it makes this argument equal 0. 3 minus 3 is 0. Square root of 0 is 0. 0 times 2 is 0. I always want to look for what makes the argument equal 0. That's the most interesting value of x. But now, I don't want to plug 1 in. I don't know what the square root of 2 is. It's 1.414, but it gives me a decimal. So I'm going to plug 2 in. 3 minus 2 is 1. Square root of 1 is 1. 1 times 2 is 2. Sometimes students forget the square root of 1. I always want to be able to produce a 1 when you got a root. But the next good number is negative 1. Because 3 minus negative 1 becomes 3 plus 1, or 4. The square root of 4 is 2, and 2 times 2 is 4. But it takes practice, making sure that you know how to identify the perfect squares. I do not want to plug in negative 2 or negative 3 or negative 4, but negative 6 works. 3 minus negative 6 becomes 3 plus 6, 9. Square root of 9 is 3, times 2 is 6. Okay? Clearly I did not plot those here. Okay? For some reason it did not get done. This graph should be plotted out. 3, 0, 2, 1, negative 1 up 4, negative 6 up 6. See if I can do it with a pen here quickly. Okay? No. All right. I will play around and get better at this. Again, the recordings will get better as we go. But you can plot those points, 3, 0, okay, to the right 2, up 1, back 1, up 4, back 6, up 6, and draw all that. Remember, again, we are looking at the top half of a parabola that opens to the left. That's what we're looking at. Okay? So there's that one. Questions on that? I'm going to say that a lot too because I'm used to doing that in class. Problem number 16. This is one of the hard ones. And again, this is why I want to make sure that we start with the domain. It's a square root. So I set the argument greater than or equal to 0. How do I solve this? You can do it just by looking at it. Or You can do it by factoring 3 minus x times 3 plus x. Set each factor equal to 0. So it's positive and negative 3 is where this equals 0. Then I just draw a quick graph of it. And I ask myself, is it going to be the area in between these two numbers or the area on the outside? Check 0. Does it work? Yeah, 0 works. 9 is greater than or equal to 0, so all the numbers in between work. That's the best way to do it. A lot of you can do it just by looking at it. If you can identify that 3 and negative 3 produce zeros, then you just decide, is it the area in between or the area on the outside? Plug 0 in, see if it works. So I know it's got to be between negative 3 and 3 are the only values I can plug in. So here's what it looks like. Negative 3 is less than or equal to x is less than or equal to 3. Bracket, negative 3 comma 3 bracket. Notice brackets on both of these because of the equal to. Why do I have equal to? Because this works. If I plug in negative 3, I get 0. That's greater than or equal to 0. If I plug in positive 3, I get 0. It's greater than or equal to 0. The range you're going to want to do after you get a picture. If I graph these points, these are the only 3 nice points that we can graph. 0 gives me out the square root of 9, which is 3. Negative 3 squared is 9. I get 0 back out. Positive 3 gives me 0 back out. This is an even function. So I graph that point, that point, that point. It's hard to know right away how am I connecting this if you don't recognize that this is a semicircle. And here's why I'm going to show you why it is a semicircle. Again, I'm trying to write down as much as possible. Why semicircle? If I square both sides, I get this. If I add x squared plus y squared equals 9. That's a circle. Center is at the origin. The radius is 3. So this is a circle. This just happens to be the top half of the circle. If I started here and worked the other direction, okay? If I got y squared by itself by subtracting x squared and I took the square root, I need to consider plus or minus. If that would have had a negative sign out front, it would be the exact same graph except below. It would be the bottom half of that circle. But we need to remember the square root of a number minus x squared is a semicircle every time. And we're going to see it a lot throughout the year. X-intercepts and y-intercepts, they're all listed right here. But again, any x-intercept, plug 0 in for y and solve. Any y-intercept, plug 0 in for x, solve for y. 18. Another very critical problem. We're going to look at a lot of these fractional exponent problems, some in the notes, some in the homework. Notice that I've taken this fractional exponent and rewritten it like this. When you rewrite a fractional exponent in radical form, use parentheses. Do the index part first, which is the index of that radical. The denominator is always going to be the index of the radical. If this was 2/3, this would be the cube root of x squared. But we always want to do the root part first. Remember, the root is the bottom of a tree. Start there. Make the number smaller. Then raise it to the exponent. So as I'm plugging numbers in, I want to think of numbers that are perfect squares. Square root of 0 is 0. Cubed is 0. I can take the square root of 1. Square root of 1 is 1. 1 cubed is 1. Square root of 4 is 2. 2 cubed is 8. The square root of 9 is 3. 3 cubed is 27. It's already off this chart, so we don't need to keep going. But those 3 points right there give me a nice picture. 0, 0, 1, 1, 4, 8. Connect them. There it is. That's what it looks like. I cannot stress enough. You have to be able to evaluate fractional exponents. And the quick way to evaluate fractional exponents is to evaluate the denominator first. The root part first. Make the number smaller, then raise it to the exponent. And I know most of you didn't do that in previous classes. You wrote this as the square root of x cubed with the cube in here. It's the same thing, but you want to do the radical part first. Trust me on this. We're going to see a lot of it. Here's a domain. written in Set Builder, and we can see the range starts at 0, goes up. But we really don't know it until we point plot it, right? Why is the domain x is greater than or equal to 0? It's a square root. I cannot take square root of a negative number. That's another reason why you want to think of it this way first. If the denominator is an even number, that's when you're going to get domain restrictions. If you have a fractional exponent and the denominator is an even number, you're taking an even root because that tells you the root. Problem number 20, even harder. Let's think about this one. It's still a square root, but we also have a denominator. So we've got both domain restrictions to consider. First of all, I cannot take the even root of a negative number. So I have to set the argument greater than or equal to 0 normally. But now this can't equal 0 either because it makes a 0 in the denominator. That's why the argument is set greater than 0. Notice when I do these quadratic inequalities, I just treat it like an equation. I solve this. I find out that the two critical points for this equation are -2 and 2. And again, I just want to check, is it the numbers in between or the numbers on the outside that work? Does 0 work? Yeah, 4 is greater than 0. It works. But if I tried to plug 3 in, it wouldn't work. 4 minus 9 is -5. That's not greater than 0. The easiest way to do these inequalities with quadratics or higher is to treat it like an equation, find the critical points, and check the intervals. We're going to do this in calculus all the time when we do first derivative and second derivative sign charts. This is the best way to do it. Most of you can just think through it. Oh yeah, this equals 0, 2, and -2. Do the numbers in between work? Yeah, if I plug in 0, it works, right? You can do it without writing anything down, so you do not have to write it down when you're doing your homework assignments. The domain here is -2 to 2. Notice now it's non-inclusive because those numbers would make the denominator equal 0. So here's what it looks like. Some students get this confused with a coordinate point. This is not a coordinate point. -2 parentheses 2. It's all parenthesized. Okay? So it will tell us when it's an interval. It will use the terminology interval so you don't get it confused with a coordinate point. The range here can be a little bit difficult. Okay? Here's how the range works. You really have to just have an idea of plugging values in. In other words, if I plug 0 in here, it works out well. 1 over the square root of 4 is 2. I get 1/2. But I don't have any other really good points to plug in. 1 doesn't work out well. As a matter of fact, I plugged in the square root of 3 because when I square it, that gives me 3. 4 minus 3 is 1. Square root of 1 is 1. So whether I plug in +3 or -3, we get out 1. 3, the square root of 3 is in between 1 and 2, so it's somewhere here, and I got to go up 1. Okay? Well, it's actually about 1.71, then I go up about 1. How do I know it goes like this? I really don't have any other options. These have to be vertical asymptotes because they make the denominator equal 0. What are the values of x that make the denominator equal 0? Both -2 and +2. So we have two vertical asymptotes, and I know there's nothing on the outside of this. This is why my graph looks like this. And I could check some more points. I could get closer to 2, but to the left of it, or closer to the 2, but -2, but to the right of it, and see that it gets larger and larger, but there's no other option but to go up. This is not a problem that they would expect you to be able to graph on the AP test without a graphing calculator. But they would expect you to know how the vertical asymptotes here work out without a graphing calculator. And we're going to practice that a lot more in Chapter 2. All right, the last part of this should go pretty well. When we're checking for even or odd, these last few problems here, I think the easiest way is to simply check opposite signs. Check opposite inputs. Now you can look at this. Some of you are going to be able to look at this and say neither, because this is an even term, that's an odd term. But it's always worth it just to check. If I plug in -1 and square it, I get 1, and 1 plus -1 gives an output of 0. But if I plug in 1 and square it, I get 1, and 1 plus 1 should be 2 here, not 3. Okay, so that should be a 2. But opposite signs do not produce same results, so it's not even. Opposite signs do not produce opposite results, so it's not odd. If it's neither odd nor even, then we write neither. Most functions are neither. Even and odd functions are unique functions. Let's do the same thing here. If I plug in 1, I get out -2. If I plug in -1, I get out -2. If I plug in 2, I get out 1. If I plug in -2 and square it, I get 4 minus 3 is 1. Opposite signs yield same output. That's even. When opposite signs produce same result, even function. Look at this. Now when I plug in 1, I get out +2. When I plug in -1, I get out -2. When I plug in +2, I get out 10. When I plug in -2, I get out 10. Opposite signs produce opposite results. Therefore, this is an odd function. What about this one? First of all, I can plug 2 in and get out 0. Okay? If I plug -2 in, I get the cube root of 4. I checked it with 1 and -1. If I plug in 1, I get out the cube root of 1 is 1. If I plug in -1, 2 minus -1 is +3. But the cube root of 3, there's no correlation. Neither. This ends up getting a lot of people because they look at it and say, oh, that's an even term. Okay, so it's got to be even. And in this case, it works, but it's there are other ones that can get you on these. So just check it. If I plug 2 in, I get out 1/3. If I plug -2 in, I get out 1/3. If I plug 3 in, 3 squared is 9, minus 1 is 8. -3 squared is 9, minus 1 is 8. Opposite signs produce same result. Opposite signs produce same result. That's an even function because it can be folded over the y-axis. Those are the solutions. We have, it's about 37-minute video, and I said between 30 and 40 minutes on these, okay? And they will get better as I'm able to edit as we go. All right?